Welcome to another lecture in construction equipment, and today we're going to be talking about lifting and loading equipment. Primarily we're going to be talking about cranes. We're going to discuss what are different types of cranes and how to calculate their loads and their cycle times and so on and so forth. So we're going to start with a review of some of the issues, the safety issues related to cranes, because again these are heavy equipment used for heavy lifting, and therefore we have to be very cautious while using them. So I'm going to show a few video clips of some crane disasters, crane accidents, and we're going to pick up the discussion following that. Here, as you can see, we have a crane lifting a huge truss for the roof of a structure, and then suddenly, as you're going to see, something with the balance of the truss causes a problem, and as you can see, the crane is tilting, collapsing, and falling down. That can cost thousands, if not hundreds of thousands of dollars when it comes to the price of the crane itself, the cost of the crane, and the cost of the steel structure it was carrying, in addition to any damages to the structure itself, to the building itself, and of course any injuries or, God forbid, fatalities. Here again it shows a crane lifting that load that was not properly secured, and as we're going to see, that load includes some heavy equipment, probably for HVAC, and it's being lifted gradually, but as you can see, suddenly it collapses and falls on a car. Thank God that there was no one in that car, but as you can see, the person was standing very close to that car, which could have caused some severe injuries and maybe even fatalities. And here's the third one. Again, a crane lifting a heavy truck. And as you can see, the truck is lifted from four corners. Actually, that's another crane, that's another telescopic crane being lifted. And there's a tag line, as you can see at the bottom, held by that person, trying to guide that load to where it should be. So far it's going well. And then you can see the tilting of the load and collapse again, that can result in severe damages. And finally, here we have a tower crane, and the tower crane was erected to build a certain structure, and then there was a storm. Let's see if we're going to be able to play that clip. Let me go back, try to play the clip. As you can see, there seems to be a storm or something, and that crane has not been secured properly, so it keeps rotating freely, and it can hit something and it can cause some severe damage. Some of you may have seen some pictures of a crane dangling from a high-rise building recently following a recent storm. So again, as you can see, the wind causes that crane to rotate freely. So now we're going to start talking a little bit about the types of cranes that we're going to talk about. Specific types of lifting and loading equipment include forklifts, man lifts, which again are used to lift personnel to perform either maintenance or repair or installations, material handlers, lift trucks, mobile cranes, and tower cranes. All of these are different types of lifting and loading equipment. The crane is the primary machine used for vertical movement of construction material. So here in these pictures we have different pictures of different types of cranes. Here we have a telescoping boom truck mounted crane, where this is the telescopic boom and it's mounted on a truck. As you can see, it can carry a heavy load because this number of axles. An all-terrain crane, again, it has a higher ground clearance, allowing it to work on rugged surfaces. And again, another rough terrain crane, pretty much similar to the all-terrain. And these are the cranes for heavy lifting, very heavy lifting equipment or lifting other materials. A crawler crane and a lattice boom truck mounted crane, similar to the crawler crane but on a truck mounted for easier motion and moving on roads and so on and so forth. And this is another view of the crawler crane with the lattice boom. Basically it's sort of a truss to reduce the weight of the boom itself and allow it to carry heavier weight. And that's another view here of the double lattice boom crane. The load is going to be mounted on this side, and we have counterweights to counterbalance the load and prevent the crane from over tipping. So crawler cranes, the full revolving superstructure of this type of unit is mounted on a pair of parallel crawler tracks. So here are the tracks, and on top of these we're going to have the full revolving apparatus that's basically the crane itself. The crawlers provide the crane with good travel capability around the job site. So again, if you have a rough terrain on the job site, muddy terrain or whatever, then you're going to be able to move with this crawler crane. It's not designed for travel on highways because of course the tracks are going to damage the pavement. So again, here's the lattice boom crawler crane rigged with the jib extension. This is the jib extension to extend the reach of the boom. And here's another jib extension. As you can see, this is the main boom and that's the extension. As you can see, it has a very far reach. It can reach higher elevations. And here's a rubber track telescoping boom crawler crane on an urban project. Now this can work on regular streets and highways because of the rubber tracks that are not going to damage the pavement. So it has the benefit of tracks to allow for better traction, and at the same time it's rubber tracks so it can move on regular roads and highways. And this is of course a telescoping boom that can be extended hydraulically to reach farther distances. And here's an extendable counterweight to increase the lifting capacity. The counterweight is here at the back of the crane, and the farther it can extend hydraulically, it offers better balance for the crane to counterbalance the load at the end of the boom on this side. For the crawler crane, some of the common dimensions, the maximum boom length can be anywhere between 100 to 400 feet, so it can be really tall. The maximum fly jib length, which is the extension, can be anywhere between 30 to 120 feet. The maximum radius for operation of the boom is anywhere between 80 and 300 feet, and the minimum radius is going to be 10 to 15 feet, so it can lift a very heavy load in that very limited minimum radius. Some of the common capacities, the maximum lifting capacity at minimum radius can be 30 to 600 tons. So 600 tons, that's a really heavy load and really heavy crane. The maximum travel speed, since this is a crawler, is going to be relatively slow. It's 50 to 100 feet per minute, which is 0.6 to 1.2 miles per hour. The ground bearing pressure, 7 to 20 psi, so it has a relatively low ground bearing pressure because of the load being distributed along the tracks, which creates a larger contact surface with the ground. PSI, of course, is pounds per square inch. So here we have a table for the cranes that shows what's the boom length, and at the different operating radii, what would be the maximum allowable load. So as you can see here, for example, if you're operating only at 10 feet radius for a 40 foot boom length, you can carry a load of 80,000 pounds, that's 40 tons. But if you extend that radius to 40 feet, as you can see, the load drops considerably to only about 5.5 tons or so. So from 40 tons to about 5.5 tons based on the radius. Of course, the longer the boom, as you can see here, for example, with the 140 foot boom, it operates at a radius of 30 feet. It can lift 15,500 pounds. and at 100 feet, that's a far reach, it can have only 1,130 pounds. So let's look at an example here. A contractor will use an American 599C crawler crane, C for crawler, crane to support steel construction of an industrial plant. The longest operating radius will be 50 feet, and the highest required reach is 65 feet. That's the vertical reach. The bottom of the boom is mounted on a crane structure 5 feet above the ground, and the hook and slings weigh 1,000 pounds. What is the length of the boom to be mounted on this crane, and what is the maximum load the crane can lift safely at an operating radius of 50 feet? So it's just a very simple geometry and trigonometry problem. We have to draw this problem. So we have here a radius of 50 feet, and here we have the reach is equal to only 60 feet, not 65, because again the boom itself is 5 feet above the ground. Therefore, if the total reach is 65, then the actual height is going to be 60 feet. So using the Pythagorean theorem, we get that this hypotenuse is equal to 78 feet. So we're going to use a boom that's 80 feet, because we have a boom of 50 or 80 and so on. So from the tables, this table for example, we're going to use an 80-foot boom, and we have a 50-foot radius, so the load can be up to 8,080 pounds. But we have hook and slings that are equal to 1,000 pounds, which has to be deducted from the total load. Therefore, the maximum safe load is going to be the 80-80, which is what the table gives, minus the sling and so on, and the hook and sling, which is 1,000 pounds, and that gives 7,080 pounds at the tip of that boom. As you can see, the problem is very simple. Now talking about telescoping boom truck mounted cranes. As you can see here, it's mounted on a truck, and the truck has outriggers. These are the outriggers that can extend to the sides to give better balance and stability to the truck, increase the width of the base of the truck, therefore improving the balance. And in this case, what's going to happen is that once these hydraulic arms are lowered down, they are lowered to an extent where the tires of that truck are not touching the ground anymore. So the full load is supported by the outriggers. And here's the telescoping boom. These are truck cranes that have a self-contained telescoping boom. The outrigger on large steel mat to prevent damage to pavement. So here you can have the wide steel mat, or like something like this. The outrigger on layered steel mats. Note the dangerous ground deformation. Again, here for example, you're going to notice that the pressure of the outriggers on the mat is going to create some ground deformation, because the ground is relatively soft. So you should increase the width of that mat to avoid the high pressure on the soil that can cause deformation and instability of the whole crane. Here the crane is raised on the outriggers, and here it has an extension jib. It could be hydraulic, it could be telescopic with an extension jib as well. Common dimensions: the maximum boom length 70 to 170 feet, maximum fly jib length 30 to 100 feet, maximum radius for the boom only 60 to 140 feet, and the minimum radius 10 feet for most models. Now let's look at the capacity. The common capacity is anywhere between 20 and 120 tons at minimum radius. Maximum travel speed 40 to 70 miles per hour. So here's the compromise, here's the trade-off that we have: relatively lower load to be lifted by that crane, but higher mobility of the crane, because this can travel on highways, so you don't want to waste much time in its transportation. Number of axles between 3 and 4. And here we have the lattice boom truck mounted crane, very similar to the hydraulic telescoping boom, but in this case we have a lattice boom which is lighter in weight. The lattice boom structure is lightweight. This reduction in boom weight means additional lift capacity, as the machine predominantly handles hoist load and less weight of the boom itself. The common capacity, again, maximum lifting capacity anywhere between 50 to 600 tons, so that's heavy lifting here again. Maximum travel speed 40 to 60 miles per hour, a little bit slower than the other one, the telescoping, but still relatively good speed, 40 to 60 miles per hour. Number of axles anywhere between 4 to 8 to accommodate the very heavy lifting up to 600 tons. The common dimensions, the maximum boom length up to 470 feet, from 170 to 470. Maximum fly jib length 40 to 300. Maximum radius for the boom only 130 to 380 feet. As you can see, this is much larger than the telescoping boom. And the minimum radius anywhere between 10 to 25 feet. For rough terrain cranes, again, as you can see, this has a very high ground clearance. These units are equipped with unusually large wheels and closely spaced axles to improve maneuverability at the job site. So it has a relatively low turning radius. They earn the right to their name by their high ground clearance as well as the ability to move on steep slopes. Usually they are four-wheel drive to allow for better traction. Here we have a telescoping lattice boom. So it has the benefit of the telescoping boom, and at the same time it's a lattice boom for lighter weight. The common dimensions, maximum boom length 80 to 140 feet, maximum fly jib length 20 to 90 feet, relatively small or short, maximum radius 70 to 120 feet, and minimum radius 10 feet for most models. The capacity is also relatively limited, 20 to 90 tons. Travel speed 15 to 35 miles per hour because of the rough terrain, and number of axles 2 for all models. The all-terrain cranes. These cranes have an undercarriage capable of long-distance highway travel. It has more than 2 axles. Yet the carrier has an all-axle drive and all-wheel steering, crab steering, large tires, and high ground clearance. So again, crab steering, we talked about that it can move relatively sideways, and all-wheel steering, allowing it to turn in a smaller radius, all-wheel drive to give better traction, and high ground clearance to be able to move on rough terrains as well. The dimensions slightly larger than the rough terrain crane, 100 to 270 feet, maximum fly jib length 30 to 240 feet, maximum radius 70 to 250, maximum radius 100 to 300, and it can increase up to 400 feet for the largest machines, minimum radius 8 to 10 feet. Common capacities, the maximum lift capacity is 30 to 300 tons, relatively high. Maximum travel speed 40 to 55 miles per hour, acceptable, very good speed. Number of axles 2 to 6 and up to 8 or 9 even for very heavy cranes. Now you're gonna see these crawler cranes for heavy lifting. As you can see here, this is the roof truss, probably for a stadium or something like that, as we have seen in the accident that we saw at the beginning of this presentation. So, and here we have the counterweights. As you can see, this is going to be very, very heavy lifting. Additional counterweight mounted on a wheeled platform to increase lifting capacity. It's suitable for building projects, low-rise structures, short cycle times. High-rise structures, it's going to have longer cycle times. High-speed, high-volume operations like concrete placement. For site conditions, you have to select the position and location where you're going to locate that crane, and the vertical reach requirements to avoid contact with power lines and things like that. For industrial projects, it's very precise. It can carry very heavy loads, working around fixed objects, and again you have to check the site conditions and the vertical reach requirements. For heavy civil projects, it can be also used for bridge construction. For example, as you can see, it's carrying the beams for a bridge. Again, it's very precise, can carry heavy loads, high speed, high volume operations, multiple work locations based on its ground clearance and its flexibility, and you have to check the site conditions and the vertical reach requirements as well. Now that we're done with the ground moving cranes, we're going to start looking at tower cranes. And tower cranes, as you can see, have different shapes, different forms. One is called the topless or flat top tower crane, like this one. The other one is the hammer-like, which has the cables extending on top of the crane itself. This is the horizontal jib. This is the luffing boom. And here we're going to have the counterweights. And this is the articulated jib, which can have a farther reach horizontally. Here are some of the main components of that tower crane. Here we have the counterweight jib with the counterweights at the end. And here's the main jib where the load is going to be located on the trolley here at the other end. Here's the slewing ring, which is going to allow the crane to rotate. Here's the cab where the crane operator or driver is going to be seated. And that's the tower or mast of the crane, which can change in height to accommodate different construction operations. Again, here's a view of that crane, the counterweight and the counterweight jib, the main jib, and the mast. Here you can see that this is self-elevating crane that can extend its height depending on the job conditions. This one is moving along rails. You can have it fixed in place or moving along rails depending on the job requirements. The cab, here we have the cab located at the bottom of the crane, and then it can climb that mast. Climbing rotating operator cab for higher tower crane. Hoisting, now we're going to look at the different motions of that tower crane. The first one is hoisting, which is the vertical lifting. So hoisting is the vertical movement of the load. The hoist cable runs from the hoist drum located on the crane's counter jib here at the end, through the jib, and then the trolley, which is the moving part on the jib, and down to the hook, which is going to be where the load is going to be attached to the crane. And that's the hoist drum with the cable that's going to allow for that load to be lifted or lowered down. The hoist cable runs from the hoist drum located on the crane's counter jib, and that's close to the counterweight here in the back. The second motion is going to be the trolleying, which is the horizontal motion along the boom or the jib, the main jib of the crane. So trolleying is a horizontal movement of the trolley along the jib. It allows for the adjustment of the operating radius. The third motion is slewing or rotation. Slewing is the rotational movement of the jib around the tower's or the mast's vertical axis. In fixed tower cranes, the slewing ring is located at the top of the tower here, and the jib slews around the vertical axis of the tower. In some cases, you might have that slewing ring located at the bottom of the mast, as we have in this picture. So another option is for the slewing ring to be located at the base of the tower, and both the tower and the jib slew relative to the base of the crane. So all of this is going to rotate. Tower cranes are relatively flexible. They can have different mounting configurations, which can vary between fixed base or a stationary base, either freestanding or braced to the building structure, because the taller the crane, the higher the wind load is going to be on it, and it might cause some instability. So we're going to have some anchors that transfer lateral loads, especially wind loads, to the building structure itself. So that's better bracing of the crane to the building. You might have more than one of these bracings depending on the height of the crane. The fixed base does not transfer any load to the building structure. So here it transfers the load directly to the ground. And here we have a tower crane based on piles. So it has to be very well position to avoid any lateral motion. Climbing, the crane can either lift itself on the building structure as the work progresses, and traveling, it can be either on rails or on wheels. On wheels are relatively rare because of issues of stability, but rails are more common. For the climbing cranes, the crane can basically self-erect itself, usually climbs through an opening within the structure, must ensure that the structure's framing has sufficient load carrying capacity to support the added stresses of the combined weight of the crane and the lifted loads. So this is within a core of the building itself or something like that. We're going to see a short video clip of a model of these cranes being erected. Here we have how the crane lifts itself, how it adds additional joints.
And then it slides up to insert this joint, and then once this is done, it moves up, and now the crane is much taller than what it used to be. So let's look at these different video clips that are going to explain how the crane can self-erect and increase its height. This is something like a time lapse that shows now we are adding a joint to the crane. It's going to slide sideways here, and then the crane is going to be mounted to increase its height. As I said, this is a time lapse, so that takes several hours to perform. You can see here the hydraulic action lifting the crane. Now they inserted the new joint, and now the whole crane is going to climb up. Here's another joint being prepared to be inserted as well. The crane is going to climb up. The joint is going to be inserted, and so on.
Good morning. Wait a minute, George. I'm looking at this thing that you...
Now let's look at another one, another clip. This shows a model of that crane. It's not a real one, but just a model. Again, looking at how the extension is going to happen. Different components. Here's the cabin. Now it shows that all-terrain crane erecting the tower crane itself. So it's first erecting the base that's on a pad to allow for better stability, a concrete pad. That's a telescoping boom all-terrain crane. And now it's going to assemble the jib on the ground. And now it's going to start assembling the mast of the crane. This is the platform that's going to be used for counterweights, and it's going to add more of these, usually concrete slabs or concrete blocks for the counterweights. Of course, the heavier the lifting, the more these weights are going to be. And now it's going to start attaching links to the mast.
And this is the platform that's going to allow for the extensions. It's open from one side. And hydraulically controlled, as you can see. So now it's going to start adding links and inserting them one by one to increase the height of the crane. And here it's climbing. That's the counter jib, which has the counterweights here in the back. And you can add additional counterweights. And now the main jib. And you connect them. And as you can see, there's going to be some relaxation, some tension in this articulation, additional counterweights. Now we're going to increase the length of that crane. Oh, first of all, the cab for the driver or the operator. Someone once described to me the best way to visualize this is like a monkey climbing a tree. So first it reaches with its arms and then secures the arms, and then the legs move up. Once the legs are secured, then reaches with the arms again. So that's exactly what's happening here. Now it's going to pick a link and insert it to increase the height. It's open on one side, as you can see. Lower it, secure it in place, and climb. So that's how the height of the crane is going to increase. You can have some bracing to the structure itself. As you can see here, this is bracing to the structure to add lateral stability, and then it keeps going up. You might have another brace to the structure as well, depending on the height, total height of the building. And there you are. And basically it at the end of the work, it disassembles itself exactly in the same way as it did, at least for the main mast. And then you're going to use that telescoping altering crane to remove the main jib and the counter jib and so on. Let's see if we have a I guess that was the second clip. Climbing cranes. Here we can see that the climbing crane is inside the building itself. So you have an opening in the slab where the crane is going to be elevating itself. Internal tower crane climbing through openings left in the ceiling of the structure. And you have here temporary shores to carry the extra load resulting from the load itself. Here are some hook attachments, so you can have either digging tools like a clamshell or an orange peel bucket. You can have hooks, different types of hooks for different types of loads, slings and so on. You can have grabs, tongues or grabs or clamps or magnets. That's usually in shipyards and car, used car yards and so on. Grapples. You can also have skips or concrete buckets. You can use the crane to pour concrete, to place concrete. You can have weights like a skull cracker or a demolishing ball, a pile driver, bottom dump platform, or load platform for bricks and blocks and things like that. So all of these are different hook attachments that can be hooked at the tip of the jib. The most important factors to be considered when selecting a tower crane are the operating radius, because once you install that tower crane, especially if it's going to be fixed in place, it's going to cost you a lot of money to install it, so you don't want to move it every now and then. So you're going to design your site layout where the crane has the maximum reach and it covers at least most of the area that you need to be covered. In addition to that, the lifting capacity. Of course, the farther you go on the jib or on the boom, the lower the load is going to be. So at the tip of the boom, the load is going to be considerably smaller than closer to the mast. And the lifting speed, especially controlling the cycle time, especially when you're placing concrete and so on and so forth. The weight of the hook block is usually considered as part of the crane's dead weight. So as we have seen with the other crane, when we had the weight of the hook and the sling and so on, we deducted that from the lifting capacity. Same thing here. The rigging system is taken as part of the lifted load. Always check the manufacturer's load chart notes, and the American Society of Mechanical Engineers standard states that under static conditions, load ratings shall not exceed 67% of the calculated tipping load, because you're going to have some wind loads, some motion of the load itself, which is going to create a dynamic load on the boom of the crane, which is going to lessen the total maximum allowed load at the end of the boom. For dynamic loads, load charts are based on the static loading condition for tipping. When the load is moved from a condition of rest or is stopped, dynamic loading will occur, and this is one of the reasons why only 67% of the static load is taken as the capacity. So you're not going to load the crane to its maximum capacity, you're going to take only 2/3 of that maximum capacity. Wind loads, again, as we have seen in one of the catastrophic collapses of cranes, tower cranes are wind sensitive machines because of their high contact surface area. Operations should be discontinued when wind velocities exceed the manufacturer's maximum permissible in-service wind velocity, which is usually in the 30 to 40 miles per hour range. So if you have strong gusts of wind, you may suspend operations until that gust is over and then resume work later on. If there's going to be a storm, then the crane must be locked and secured so that the boom does not rotate, as we have seen in the previous video clip. Again, the American Society of Mechanical Engineers standards require that for structural competence, dynamic effects associated with hoisting and slewing and wind at maximum service velocity be considered. So there's no safety factor requirement as with the tipping conditions in this case. It's again left to the consideration and the expertise and the experience of the operator and the project manager, who should stop the operation if there's any danger to people or to property. Because of how tower cranes are load rated, and from experience it's recommended that a 5% work margin be maintained on every tower crane lift. So if the weight of the load is 15,000 pounds, the weight of rigging is 400 pounds, so the total weight is 15,400. We're going to allow an extra 5% working margin, which is a factor of safety of 1.05. Therefore, the required capacity for the crane, which can be obtained from the table, is 16,170 pounds. And here's a sample of the tower crane loading tables. Again, it shows for different boom lengths or lengths of the jib and different operating radii. Of course, the more the radius and the more the length of the jib, the lower the load that can be carried is going to be. Here at 124 feet, we can see with the operating radius of 98 feet, it can carry almost up to 10 tons, 22,050 pounds, whereas at the 200 feet, with the 200 feet working radius, it can carry only about 4 tons. And that's basically it for cranes. As you can see, the crane problems are going to be very simple. It's going to be related to selecting the proper type of boom or jib length, knowing the operating radius and knowing the load, or based on a given length of a jib and based on a given operating radius, we're going to have to determine what is the maximum load that can be carried at that specified radius. I'll see you in another lecture related to construction equipment.